In this video, I'm going to take that Ravpower power bank that was sent out to me to evaluate and test, which I did in the prior video to show you, yes, it can charge multiple devices, and it does a pretty good job doing so. This time we're going to take this thing apart and see how well this one's built. And the build quality might actually surprise you. It's not bad at all. So we're going to start out here by prying open the cover. So I've got to get my screwdriver into the edge here. These covers are all popped together with plastic clips. So you just kind of work into the corner here, and it will eventually pop apart and reveal the goodies inside. Now I am being cautious here, as I don't know whether this uses cylindrical type cells or whether it's using a polymer, lithium polymer type, and of course the last thing you want to do is poke one of those things, because you'd have major flames everywhere. Those batteries are notorious for bursting into flames. So I'm being extra careful here when I'm opening the cover up on this thing until I actually can see what's inside. And when I was able to peer in, I noticed that they were cylindrical type of batteries, which kind of put my mind at ease for the actual construction of this unit.
Okay, so here's what we've got in this thing. There's cylindrical type cells, which is good. Yeah, I can. There we go. Okay, this is the working guts of this unit, as you can see. And what we have in here is we have 5 cells. They're all connected in parallel. There's a little temperature sensor right here, which is a good safety device on these units. So if I remove the little circuit board here, let me just take out one of these screws. One of them I kind of broke off, so I'm going to have to glue that back down, but I'll remove this screw and try not to drop it into the circuit and cause a short circuit, because this thing is still energized. Okay, now we can lift the entire unit out. I'm just going to remove this other screw here, and for safety's sake I'm just going to disconnect. I'll disconnect the positive lead here, just so that this is not energized while we're poking around on the circuit, because as it sits right now we still have power. And if I press the little button, wherever the little button might be on this thing, it will turn on the light. You see? So I'm going to disconnect the positive lead here from the battery. Okay. Might as well disconnect the negative lead too. So this is the inside of this Ravpower. As you can see, it looks to be really well constructed. It's got some good quality cylindrical type cells. There are 5 cells. They are all connected in parallel. So our input voltage on this should be about 3.6 volts, I believe. It should be. We're fully charged now, so let's take a look at the voltage that we've got on the cells here. And we have 4.1, which is pretty normal. I'm of course connected backwards. That's the positive side here. 4.1, and that's pretty normal. These cells are 3.7 volts, but they're not operating under any load, and they are fully charged. On this little circuit board here, we're going to have an inverter type technology to step the voltage up to 5 volts. It's going to take the 5 volts from the charge input and drop it down to the 3.7 volts that are normally required on the cells to charge them. They'll charge a little higher. They typically charge them around 4 volts or so. And this will then take this 3.7 volts, because under load that's what they would be, and it will step it up to the 5 volts required for the USB output. But there's our little circuit board there. The build quality doesn't look to be too bad on this thing. It's all nice surface mounted components. Got our B plus input and our negative input here. Let's look up the specs for these batteries and see what the cells are rated. So an LGA BF1L1865, that's a cell made by LG. They are rated at 3350 milliamps each. Being LG cells, I would say that's a very good thing. LG makes some fantastic cells. That's what's used in a lot of the electric cars. For example, all the General Motors vehicles, the Volt and the Bolt and so forth, they're all using LG chemical cells in them. They're not cylindrical cells like this. They're a flat modular cell, but they're still LG cells. The original ones were actually made in Korea, and now they make them domestically for those cars. But this battery pack seems to be very well constructed here, and I was really happy to see a cylindrical type cell in this and not one of those lithium polymer batteries, because we all know the problems that lithium polymer battery packs have. They have a tendency to go supernova. Puncture them or drop them or damage them or crush them, and you're going to have a problem. Whereas something like this, you're not. Let's take a close look at the fusing on this and see how well protected this little circuit board on this unit is. I'm going to reconnect the battery so we can do some voltage measurements on the board itself. Okay, we now have power once again. If I click the button here, and this little thermal sensor is going to go back underneath this tape here when I'm done. This is obviously so that if the cells were to overheat either during a discharge or a charge cycle, it's going to shut them down. But let's do some voltage measurements here and just see what type of voltages we get through the various components, because there's obviously going to be a boost circuit in here. The circuitry here is going to operate as a boost network, because as you can see, we have 4.17 volts there, but at the USB terminal, when it's operational, which it shouldn't be now, it should be in shutdown mode right now. Oh no, it is, got 5 volts. So even when the unit itself is not powering anything, the buck converter, the boost converter, is giving us the 5 volts. So even when the unit is not powering up a device, there's 5 volts available at the terminal here. As you can see, 5.35 volts, which is being generated by the inverter on board. Let's see if we can get a look at some of the ICs on here and just see what they are. Here's an interesting observation. If we measure the voltage across the output for the USB, 5 volts. If I measure from the ground to the negative pin of the battery, I have 0. If I measure from the ground to the positive pin of the battery, I have the 4.17. If I measure from the positive terminal of the USB to the ground, I have my 5 volts. But I've got only 1.1. I know my probes are reversed, but I've got 1.1 volts from the positive terminal of the battery to the positive terminal of the actual USB output. So what we've got in here is we've got a circuit that gives me a 1.1, and it would give me a little more because when these cells drop to 3.7 volts, which is their nominal working, our boost circuit is going to increase the voltage. There's a series of 8205 ICs on this board too. These are 8205s, these ones. See what they do. Okay, these 8205, they're 8205A. They're a B series battery protection IC. And, well, let's just open it up here. Seco Instruments Group, it says here. And this series, the 8205A and B series includes a voltage detection circuit with high accuracy and delay circuit. It makes it possible to monitor the status of 4 or 5 series lithium-ion rechargeable batteries. These ICs are suitable for protecting rechargeable lithium-ion battery packs from overcharge, overdischarge, and overcurrent. So there's your battery protection right there, these ICs. And there are 5 of them there, looks to be. Let's see what other ICs are in this thing. So here's our inductors here. These are 1R5 inductors. These are part of the boost converter. So this is where our voltage is made up. Our battery protection is through these ICs over here. And this is our boost. And I'm just looking to see where there should be a MOSFET transistor. I believe that is probably this one, right? One of these ones down in here. I can't see the number on. See if I can get my magnifier and get a close look at this. So this is it here. It's a dual MOSFET. It's an 8205. This is our MOSFET down here. So this is working in our boost converter circuit to step up the 3.7 volts from the lithium cells to the 5.1 volts. It's all going to be controlled by probably this IC down here, which I can't find any info on. But this is going to be the boost circuit regulator. And I would think that this circuit over here is probably the charge circuit regulator, because this is where the little thermal sensor is. And lithium cells tend to heat up when they're charging. So this is providing feedback for the charge current to shut down the charger. I'm guessing, because I don't have a schematic for this thing, but that's your battery protection. There's your MOSFET, dual MOSFET, and you got a couple of little inductors here. This is what boosts the voltage up. And the reason why I think we probably have 2 of them is because we have 2 separate outputs. We have 2 separate channels that are independent from each other, so that you can charge 2 different devices. Anyway, this is not a bad little unit. I was expecting it to be a lot cheaper than it was, but I'm quite impressed with this thing. I think I'm going to put this thing back together. So to put this unit back together, just put the circuit board back in place and attach it with the 2 screws. Place the sensor back on the battery, tape it back down. Now this is a critical part, because this is what's going to sense the temperature of the cells while they're charging. And we'll reconnect the 2 wires. Okay, there we go. We're reconnected. Now we can test this thing. I can put some load onto this. We'll load down the, I'm not going to load down the cells themselves, because I don't want to bypass the overcurrent protection. So I'm going to load it down with some USB devices that draw a bit of power. So let me go grab some stuff that we can plug into this thing. So I'm going to plug my little old Kodak I used to use this camera as a dash cam at one time. It's a little Play Touch, little HD camera. It can be powered up with a micro USB, and it draws about 2 amps. So let's see if this will power this camera up. This battery is not charged in here at all. It's completely dead. I can't remember where the heck the power switch is on this thing. There it is on the side. See, it's been so long that this thing hasn't been used in forever. But hey, it's a nice little camera. It's a little 1080p camera. And get the SD card, and we'll put an SD card on this thing. Tells me there's enough space on here for 3 hours and 45 minutes of recording. I'm going to hit record. I start recording. It's actually a nice little camera. I bought this years ago, 50 bucks, and well, it actually records very well. It's nice and compact, right? A little Play Touch. Nice little camera. We're going to let this thing run here for a while, and I'm going to go get something else to load up on here as well. Okay, what I've done now is I've just connected up an old meter. This is my really old Radio Shack meter here. You can see we're drawing, I reversed the polarity, but it doesn't matter. We're drawing about 0.5 amp here off of the batteries. If I put this thing into record, it's now going to go up to about 1 amp of current that we're drawing. So we're drawing, say, 1.06 amps of current off of the batteries now. And if I measure the voltage with my voltage meter on the other meter here, we'll see that our drop our cells are now putting out still 4.13 volts. We're drawing 1 amp from them. I'm not measuring the current that's actually being drawn over the USB, which will be probably slightly less than 1 amp. Each of these channels, one will put out 2.4 and one puts out 2.1 amps, I believe. Let's see here. Yes, this is the 2.1 amp that we're plugged into. This one will do 2.4 amps maximum. But as it sits right now, we're drawing just about 1 amp off of the cells themselves. So I'll let the cells discharge at this rate. And I'm going to go grab my phone, and we'll plug the phone in here as well, and we'll see what type of power we can draw on this thing, charging up a phone and running this camera. We'll see what type of current we can actually draw from the battery here. So let's plug in the second USB port, and we'll plug that one into my BlackBerry Priv. Okay, I've got the flashlight going here. I've got my phone charging, and I've got the camera recording, and we're now drawing 2 amps from this battery. Okay, down to 2.5 there. Oh, hold on. .07, 2.06. So we're loading this thing down here now. We're gonna watch this thing and just see. I'm not gonna obviously keep filming here, but we'll see how long this thing goes and let you guys know how long it's gonna take. I'll start my little timer up here again, and we'll keep count on how long it takes to charge the battery. Still drawing 1.73 amps here, charging the phone. We'll check the battery. We'll check the voltage drop on the cells here and see how they are performing. Still at 4 volts. Been going for 34 minutes now. So performing nominally. I've now disconnected the current meter, and I'm just going to power it directly through the inverter here. And the reason being for that is that my test leads here, I've got a test lead that's broken, and every so often I move the thing and I cut it off. So we know what the current draw is for drawing this, for running this camera and charging my phone. We can just monitor the voltage drop here. We're at 4 volts now. We're in 37 minutes. Here's something I think you guys might like to see. We'll take a look at the buck converter here. So we're just gonna probe the one of the chokes here. This is the buck converter. We'll look at the other side of that that coil, and oops, we'll measure this one. And there's the square wave. So okay, the other side was the filtered side, but here's the buck converter. As you can see, what it's doing is it's creating at 198 to 200 kilohertz. The frequency is actually shifting slightly. The second channel doesn't need to be on here. We'll just turn it off. But we're able to look at the PWM signal from the buck converter. So this is what it's doing. It's switching on and off, and we're picking up the induction of the coil. This is where we're getting our boost to boost our 4 volts from the batteries up to 5.1. And here's the other one here. Should be the other coil on this side here. I think this is it here. So we got 2 of them operating at different frequencies because there's 2 different current draws here. If I turn on this camera, okay, and oops, I'm in video mode. If I hit record, we'll see the frequency change as we've just added more of a drain. If I turn this thing off, see the frequency drops now because we're not drawing as much power on this one. So we have two independent converters here. Now this one's dropped down to 43 kilohertz. If I turn the camera back on, okay, we look at, this is the converter that's powering the camera. It's running at 200 kilohertz now. The camera's in charge mode. If I put the power on, we'll see that this is going to change as it's now drawing more power. And if I press record, we'll watch the waveform. Oops, that's in still camera mode. Let's go back to video. And I press record, and you'll see the waveform now changes again. So what it's doing is it's regulating the voltage. It's changing the frequency to regulate the voltage going to this port. So that's the converter for this side, channel 1. And the other converter over here, as you can see, it's operating at a much higher frequency because this is drawing a lot more current to charge the battery up here. And we're at 56% of a charge right now on the phone. If you look at the voltage drop on the batteries right now, this thing's been running for the last hour and a half or so. We're down to 3.9 volts. So our battery voltage is starting to drop a bit as the charge is being dissipated from the 5 lithium-ion cells. To illustrate how a buck boost converter works, you have your voltage source. In this case, it's Vs. You have your switch. In this case, it's the MOSFET, which is indicated by the S on the schematic. A diode, your inductor coil, followed by a capacitor and a resistor load. Now, there are different designs of it. Some of them wire it slightly differently, but this is basically how it operates. And the switch operates at a high frequency, and basically what you're creating is you're creating a DC to DC inverter, a DC to DC converter, a simple switching power supply that does not require a transformer. And depending on the winding of the coil and the capacity of the capacitor and the frequency you operate, you can vary your voltage up or down depending on the design. If the circuit is used to reduce the voltage, it's typically called a buck converter, and if it's used to increase the voltage, it's called a boost converter or a buck boost converter. And again, you can vary the efficiency, vary the output by changing the duty cycle and changing the frequency at your switch. So these are typically used in
low to medium current requirements. Devices that require a higher current, typically they would use a full-on switching inverter with a full transformer. If we adjust our scale here, we can see our waveform, and we're on the 2 volt per division. So here's our voltage. So 2.4, showing just under 6 volts here on the pulse width modulator for the buck converter. So it's just creating a square wave, and if we go to the other side of the coil, or the other side of the inductor, well, we won't see anything. The other side is typically connected to the power. One side's connected right to the battery, the other side's connected through the MOSFET. And it's the effect of the MOSFET opening and closing which creates the magnetic field that it forms in the coil. So when the transistor, the MOSFET, turns on and off, what happens is you're pulling your voltage across the coil down to ground, and then it releases. So as the transistor kicks in, we'd normally have 5 volts because the one side of the buck converter, one side of the coil here, is going right to the battery. So you've got your power coming in. Well, it goes to that side, and it goes to this side over here on these inductors. The other side of the inductor, that side and this side, go to the MOSFET transistor that's switching back and forth, which is this one down here. It's a dual MOSFET. So as the MOSFET transistor switches on and off, it creates a higher voltage than the input voltage, because the input voltage is your battery voltage. So as I say, we're getting about a 6 volt swing here, and this is just the action of the magnetic field being formed when the transistor is in the on state, and then when the transistor goes to the off state, you get the collapsing magnetic field creates a higher voltage in the inductor, which is rectified, and that's how a boost converter works. Simplified. So as I put my finger on the converters here, the converters themselves are warm to the touch. The cells themselves are dead cold. That IC is a little bit warm. Those ICs are cool. MOSFET is cool. This thing's been running now for just about 2 hours. The battery is almost fully charged on my phone at this point, and my battery was quite low when I started. Let's take another measurement here. Our cells are down to 3.8 volts. If I look at the charge status light on here, it's still showing all 4. So the battery is still showing to be full. So we haven't even started to tap into the reserve yet from these batteries. This time when I started this test, the cells were fully charged. I charged these overnight. So the first test I did, I put a charge on them for about an hour. So I don't know that my cells were completely full. But now the cells are completely full. If we look down at the scope here, this is the converter for the camera side. Now what's happened on here now is this camera, which is still recording, the battery has now come to a full charge on this one. So it was charging the battery at the same time as the camera was running. The battery has now come to a full charge, and you can actually see the duty cycle here is changing slightly as it's regulating. And we look at the other side here. This is the one for the phone. As you can see, the duty cycle is different and the frequency is different because the phone is drawing obviously different amount of current. This one's operating at about 290 kilohertz, and this side here is operating at 719 kilohertz. That seems awful high, but that's what it's showing.
Now if I unplug the connector here, we'll watch what happens. If I unplug it, okay, it goes to sleep. It's still operating. The switch is still operating because there is still 5 volts here on the terminal. But as you can see, the frequency drops right down. So even when you're not drawing power, this thing still, the buck converter is still actually running on this thing. So there is power on the actual connectors themselves, which would make you wonder if this thing's going to actually draw the batteries down if it's not being used. And you would think because the converters are running that it would, but I have a feeling that it probably, if it hasn't been used for a period of time, it probably goes into a sleep mode and shuts the power off. But this one here is still running because of course we're still operating the camera on the side. If I switch it off, you'll see that the duty cycle will change. And if I shut it right off completely, when it shuts off, because the battery is fully charged on this one, oh, it's going back into charge mode here for a moment. But it went off there for a minute, and now this has come back on just to finish its charge cycle. If I go back to this side here and I plug in the phone, when the phone starts charging, there we go. Duty cycle changes as the unit ramps up to send more energy over to the phone. Anyway, I think this will now complete this teardown on this unit here. There's no point in continuing on this. We know how it operates, and we know that it does live up to what they claim as far as capacity goes. We've been able to prove that by actually looking at the actual cells and proving that the capacity of the cells combined is 16,750 milliamp hours, which is what they claim on the box here. Hope you guys enjoyed this video. The first one was done just to satisfy the vendor that they wanted to see this thing working in operation, but I know you guys wanted a little more, so hopefully this one here has satisfied your desire to see what's inside this thing and check out the build quality. Can't fault it. It really is looks to be a pretty good unit for the price. I'd like to see what some of the other ones look like, but just the very fact that this thing doesn't use those lithium polymer cells lets me sleep at night, because you know that these ones here aren't going to go up in flames on their own. You don't have to worry about one of these ones bursting if it gets dropped or stepped on or crushed or whatever. It's going to be hard to crush one of these cells. They're a little bit better quality. Anyway, thanks for watching. We'll catch you in the next one. Bye for now.